All right. Well, thanks everyone for joining. My name's Peter Argue. I'm on the Flow protocol team. I've spent the last year or so working on a new protocol for syncing execution data amongst the nodes and on the staked and public networks. I've also spent a bunch of time working on BFT and hardening the protocol for allowing permissionless access nodes, which will be coming very soon. So that'll be a possibility for any of you that are interested in that. And so today I'm going to give somewhat of an overview for what the Flow Execution Data Replication is solving, how it works today, some improvements that we can make, and some various things that's going to unlock for us going forward. So I'll go ahead and jump in. So first, the main goals that we're trying to solve with the execution data is we have a lot of data. We have a multi-node architecture, and we want to get the data from the nodes that are executing transactions out to the edge where people want to actually view the data for the blockchain. So effectively get it from execution nodes to access nodes. And we need to do this in a way that's trustless. We are working towards a fully permissionless blockchain where every node on the blockchain can join without any kind of interaction from the service account committee. And so we need to be able to do it in a way that we don't have to trust any single actor on the system. And then it needs to be scalable. So we need to be able to scale this to lots of data and also many nodes that need access to that data. And so just how this presentation is going to go. I'll walk over some of the challenges that we're facing today that we needed to overcome with the execution sync, where we're at currently. I'll talk through a bit about how the execution sync works itself, and then look into some improvements that we see to make in the future to make it more scalable, more reliable, and then some various features that will unlock and capabilities that we'll be able to start to build from there. So probably the primary challenge is the amount of data that's stored on the blockchain. And so when we talk about data on the blockchain, we kind of have two buckets. We've got the consensus data, so that's the blocks and results and signatures and all that sort of stuff. All the things that are needed for the consensus nodes to verify the state of the data or of the blockchain, and for other nodes to coordinate on verifying that. And then we have execution data, and that's pretty much everything else. So it's the specific values of data stored by smart contracts, it's account balances, it's all of the events, the results of transactions, the transactions themselves, and then all of that data going backwards in time. So there's like the point in time snapshot of what the current state of the blockchain is, and then there is what was that in block -1, -2, -3. So today that adds up to about 225 gigs at a point in time snapshot of the execution state, and that's just for the registers and proofs that go along with the data stored in smart contracts and account balances. On top of that, there's a bunch of data, including events, transactions, the historical state, as I mentioned, and so it adds up to quite a bit over the course of a spork. And then obviously, day to day, we're adding more data to this. It grows over time. More accounts are added, more account balances, more NFTs. And so it grows over time, and we need to find a way to get that synced across all of the nodes quickly. Another challenge is that Flow's novel multi-node architecture. So on most blockchains, you've got a homogeneous node type, and so that each node has all of the data, and that means they can all sync from each other. And so there's a large number of nodes that can sync, and then and so there's a larger pool of nodes to pull from. In the Flow case, there's a small number of execution nodes. So currently we have 7 execution nodes. There's a much larger number of access nodes. I think we're over 100 now. And then when we get into the observers and nodes on the public network, that kind of grows and compounds from there to much larger numbers. And the goal would be that we should allow execution nodes to focus on executing, and allow the edge nodes to focus on sharing the data. So finding an architecture that allows us to minimize the impact on execution nodes for the syncing of data. So that brings us to where we're at today. So I imagine everyone on the call that uses Flow and is kind of familiar with the APIs and how it all works. But effectively how it is today is we've got our execution node kind of at the top in orange. It's executing data. As it's executing the data, it's uploading it to a Google Cloud bucket. There's options for Amazon Cloud too for execution operators. So it's effectively uploaded to cloud storage. When access nodes want to access any of the data that's part of execution state, they actually query the execution nodes. And so any requests for executing scripts or getting accounts or getting events are proxied from access nodes to execution nodes. And then further, if you're running an observer, observers aren't allowed to participate with the stake network, and so they're querying access nodes. And so you query state on an observer, it queries the access node queries the execution node. Archive nodes are a little bit special in that they have the state and they can query it from their own local state. However, they're syncing all that data from the Google Cloud bucket. And so they have their own little point of failure there. And so, yeah, in orange is the execution data flows, and then the consensus data flows in blue on this chart. So a couple of problems with that. One, all of the nodes, like in all of those cases, everyone needs to trust execution nodes. And so today that's probably okay because there's a small number of them, they're permissioned, we have business agreements. Over the long term, that assumption is going to change. They'll be fully permissioned or permissionless execution nodes. They could be anyone. And so having a trust relationship between people that want to see the data and the people that are generating the data is not great for stability and security. It also funnels all of the load for accessing state to the execution nodes. And as I mentioned, there's relatively few execution nodes, and so there's just a higher demand on them across the network. And which means that we need to find ways to scale that. But unfortunately, execution nodes are very large already. They're running hundreds of gigabytes. They're running with hundreds of gigabytes of memory. Very large machines, and so horizontally scaling that number is very expensive, and it has a large energy and environmental cost as well. And then the robustness. So if access nodes all have to go to a relatively small number of nodes, there's more bottlenecks for that data and fewer. It's easier for one node going down to take everything else down. Same with the GCP upload. Is we've got a relatively small number of nodes uploading, so the number of seeders of that data is fairly small. So that brings us to execution sync. So this exists today. We're rolling out the usage of it, and so you probably haven't heard. You may not have heard a lot about it. There was a flip. Kind of discussing how it works. There's a link to that at the end if anyone wants to see it. But this will kind of walk through how it works, how it can be used, and then we'll get into some more details about that. So at its core, it's built on top of Bitswap. Bitswap is a protocol built by the Protocol Labs team. It powers the IPFS. Many people probably interacted with that through NFTs and various things in the crypto space. That is built on top of libp2p, which is also the networking stack that we're using for Flow. So that worked out pretty conveniently. And a way to think about it, if you're not very familiar, is it's kind of like BitTorrent, but instead of a swarm that's working around a single file, it's working around an arbitrary data set. And so you would register data with this swarm, in this case, the flow nodes, and then you can arbitrarily access chunks of that data from any point. So one of the things this gives us is it's a very scalable platform. It's scalable both in terms of the number of bytes that you can represent and transfer reliably, as well as the number of nodes that are allowed to participate. Reliable in that it's synced amongst many peers, and there's protocol that allows those peers to kind of manage which peers they trust and want to work with, as well as make requests and make requests out to multiple peers, and kind of manage the gossip, or not gossip, but the way that they're fetching that data amongst the full network, and trustless, which is one of the key parts here. We'll talk a bit more about that. So first on the data scaling, the way that data is represented in Bitswap is very similar to the way that a Merkle tree works, except the hashes of the data are part of the content of the payloads. And so effectively how it works is you would have, in Bitswap they call it blocks, but we've renamed the terminology for our purposes to blobs, because block becomes confusing when you're dealing with the blockchain. There'd be too many overloading of that word. So we've called it blobs. You'll see that word used throughout here. But when I talk about a blob, I just mean like one of these rectangles, or one of the smaller rectangles. So effectively, you pack a bunch of data into one blob in the Flow blockchain. One blob is 1 megabyte. That's kind of sized to fit nicely within the libp2p limits and some constraints on the Bitswap protocol. And so if you have less than a megabyte of data, that fits all nicely into a single blob. It's easy to, and you transfer that one. If you have more data than that, how that works is you would take your full serialized data, you see it here, and then you would break it into 1 megabyte chunks and take a hash of each of those 1 megabyte chunks, and then include those hashes into a root chunk or a root blob. And so then the root hash of that blob, or the root hash of, you could think of it as kind of like a Merkle tree or a Merkle structure, that would be the hash of the table of contents blob, the blob full of hashes. And so this kind of scales out nicely and is well optimized for a use case where you're writing once and don't need to recompute the hashes. So with a single blob, you can get up to 1 megabyte. If you have one blob that's full of hashes, then you could represent 32 gigabytes. And then if you have, say, a third tier, so you would have, two full tiers, so 32 gigabytes of hashes, you could represent up to 1.1 petabytes, all addressable via a single hash. And so, yeah, it's kind of like a file-based Merkle tree that's optimized for sending data over the network. The general data structure that we're using, so this is how it is today. So we've got a root block for the whole block, and so it contains the block ID and then a list of CIDs for each of the chunks within the block. And so if you're not super familiar with the way that Flow executes the transactions, we take all of the transactions that are going into a block and break them up into collections, and then each of those collections gets a chunk, and so the chunk contains some information about the execution of those transactions within that cluster. So down here at the bottom, you can see, like, within the chunk data, you've got the list of collections, the list of events, and then the try update. And the try update is basically the changes to state, the register updates for all of the transactions. And so you get all of your chunks. You create hashes of those. You serialize it all into the data structure shown above. You collect all of the CIDs. You put them into the root data structure, and then you take the hash of that, and then the hash of that is included in the execution result. And so the root of all of the data that goes into execution sync is committed directly into the blockchain, and then verified by verification and consensus. The caveat there is that we're currently not verifying the execution data hashes on the live network today. That'll be coming very soon. But when in this presentation, I'll kind of talk about it as if that is happening today because it's more convenient. It's kind of a solved problem, but that is what that will be coming soon, and it'll be built in. So one of the nice features of this is that one of the nice features from the trustless perspective is that verification nodes can verify the root blob pretty efficiently using its current setup with minimal additional overhead. The only extra thing that they really need is they need that root execution data, so the one that includes the block ID and then the list of the CIDs for all of the different chunks. And so they're already reproducing the chunk locally, so they don't really need to sync a ton of data for that beyond what they're already doing. And so they can then reproduce the hash from their own chunk and then confirm that the hash from their chunk matches what was in the root block, the root execution data, the block execution data root, and then verify that that one's hash is correct. And so when you go across all verification nodes, you've now verified the hashes for all of the chunks and verified the hash of the whole thing. And so it fits nicely into the chunk verification model that we have today. And then as we're trying to access this data, so now we've produced it, verified it, and we want other nodes on the network to be able to consume this data. Because of the Merkleized structure, it becomes very easy for them to verify. So if I am say I'm an access node and I want to download it, I grab the root execution or the block execution data root CID from the consensus data. I then can just download that or request that from the nodes on the network. I know that I got the right value because the key that I'm using is the hash of the data. So I just can hash the data locally, compare it to what the key I got. And then if I wanted to just get a subset of that data, I could download a subset of that data and verify just that hash of the piece I got and compare it to the root. And knowing that the verification nodes have already verified all of this data, I can trust that it's correct without having to recompute all of the hashes myself. So that lends nicely to sharing it amongst the many nodes and doing it in a kind of a scalable way, but it also lends nicely to sharing this onto the public network where you can't trust any peer on the network at all. And therefore, being able to get data from peers in a way that's completely trustless is very important so that we're not reproducing a trusted relationship between the staked and unstaked networks. So today, the way this kind of scales is we have execution nodes. Those execution nodes can configure a list of access nodes that are allowed to sync from them. By default, that's not used, but in the world of many access nodes, that could be a beneficial way of scaling to reduce load on execution nodes. And so you could kind of see a fan out where data flows from execution nodes out to access nodes. Not pictured here would be the observer network. Not pictured because that's currently not enabled for the observer network, but that's kind of how this would flow. One of the problems with this is that execution nodes are still responsible for sending 100% of the data to the first tier of access nodes. They don't have to send it out to all of the access nodes, but they're still responsible for sending it out to the first tier. And so there's load put on their systems that's not being used directly for executing transactions and improving the performance of transaction execution. That's being chewed up on syncing this data. So next I'll talk a bit about some improvements and where we can go to help solve a few of the problems that we've kind of come across along the way. One of them is solving the scaling problem. So as I just kind of mentioned, even with a tiered system where execution nodes don't have to sync to, actually, I guess one important point to mention here. So I put the tier underneath these connections. And so how effectively that works is this group of nodes all talk to each other for the data. And so if, say, this first access node gets the data first, then the second access node can get it from either the first access node or the execution nodes. And then say the third one comes up a month later and it's syncing all of the data, it could get it from any of these nodes. So all of the nodes in this set are a network, and they can all sync data from each other. And then on the tier 2, it's the same. It's just these two groups here. And then obviously you get out to the public network, and it would be a much larger set. So I guess that an important thing to note is that these nodes all form a swarm. It's not necessarily a push method. It's just these, say the tier 1 nodes here would be the first nodes to have access to the data, and therefore the first set of seeders. And then once other nodes have some of these blobs, they can start seeding it as well. All right, back over here. So in trying to scale this out to more and more nodes, one of the things that would be very important is to reduce the amount of data the execution nodes have to transmit even further. And so one way to do that is with verification nodes. So I talked about a little bit earlier how verification nodes are reproducing all of the data for the execution locally. So the only thing they're actually syncing from the execution node is that root, the block execution data root data structure, and they need to sync that anyway for verification. And so for verification nodes to seed data to the network, they actually need no additional data from execution nodes. And so a really nice benefit of putting verification nodes or adding verification nodes to the seeding of this data is that you can get it effectively for free from the execution nodes perspective. There's also relatively a large number of verification nodes. So today on the mainnet 21 network, we have 7 execution nodes and 84 verification nodes. And so with that, there's already whatever that is, like 12x more verification nodes than execution nodes, and all of verification nodes have partial access to that data and can sync that partial access to other nodes. And so shown here, verification nodes could sync that directly to all of the access observer and archival nodes. We could also form a tiered system depending on the characteristics of what we want to do here. But what would be important would be to have the verification nodes be seeding the data to edge nodes and not execution nodes directly. Yes. Yeah. And then we can help a little bit more by partitioning the data. And so the goal for this step would be to reduce overall network load. So basically reduce the amount of data that's actually being transmitted. So if you recall in the previous slide where I showed the data structure, each chunk had a single hash, and all of the data for that chunk was included in that hash. And that included both the register updates and the events and the collections. So if you wanted, say, just the events, or you wanted just the try update, or just the collections, you still have to download that full set of data for the chunk, and then verify that full set of data for the chunk. And so you may be downloading, you know, I don't know, a couple megabytes worth of data just to get 20K of it that you actually care about, and then you throw the rest away, and you've added load onto the seeders, you've added load onto your own machine, and costs per network and all of that. So if instead of that, we could repartition the data so that each of the chunks of data was independently hashed. You have some small cost upfront in the generation of the hashes. There's additional hashes to generate, but you significantly lower the amount of data that is needed to be transmitted in the case where you have many nodes that are only interested in partial data. And so this is very likely once we get into syncing the data to the public networks. A good example are archive nodes. So archive nodes today will sync the full data set, but really all they care about are the try updates. They want to follow the execution, so the changes to the blockchain state. And so they really only need those changes. They don't need all of the events and collections and everything. They don't need to download the transaction script from every single transaction, a list of signatures and everything. They just need the updates. And so given that all of this data has already been hashed by or verified by verification nodes, for a downstream consumer, even if it's 5 nodes down the chain there, all they need is the root block there, which is guaranteed to be under a megabyte, and then the specific chunks that they need. They can extract out say, I want all of the events from the block, or I want all of the events from this collection. They can grab the CIDs from all of those and request just that data. And then they end up downloading a significantly smaller set of the overall blockchain data. And so this is all kind of hitched on it's all kind of enabled by the fact that verification nodes are pre-verifying, and that we have a Merkleized structure built by using the kind of the table of contents root blobs there. Okay, it looks like, yeah. So 2 more benefits. I think I talked about the first 2 here. Another benefit is, say you're an access node and you want to share events with clients that are connecting over gRPC. Eventually in the protocol, we'll have a way to produce proofs of all of the data that access nodes are providing, and that for light clients to be able to verify those proofs. In the medium term, that's not really possible, and so there's a trusted relationship between clients that are connecting into the gRPC interfaces and the operators that are running them. But with the execution, with this protocol, the access nodes or observers or archive nodes, whoever is running it, could allow for clients to verify that the selective parts of the data using the same method that observers would if they're using Bitswap directly. So if you download, say, the actual serialized data in a gRPC like protobuf format of the actual structure, not even necessarily the serialized like CID data, Bitswap data, you can still recompute the hash locally and then compare the hash that you got to the root blob. And so the verification, the Merkleized verification of the data from execution sync could actually translate across to gRPC and other API types, adding some like ability for clients to get data in a trustless way before we have a fully fledged proof system available. And it also allows collection nodes to participate. We haven't really talked much, and we haven't run any flips on or anything like that about having collection nodes participate. But one unlock that we could have by partitioning the data further is that we could now allow collection nodes to participate in syncing their collection with access and verification nodes. Whether that actually gets used in protocol during the execution flow, or if it's just as here's another group of nodes that can seed, is not determined, but it's another group of nodes that could help share the load. So for a few things that this kind of unlocks, so execution sync in general will help unlock a Trie-less Archive node. So today, the archive nodes, if anyone's been following that very closely, they run on large machines. They're effectively execution node sized machines. And the reason for this is they have to load the entire 225 gigs of state into memory. And they're doing this because they're downloading all of the data from Google Cloud. And that's an inherently trusted relationship. And so rather than trusting all of the data in there is correct and it doesn't have any issues, maybe there's no like little bit flips or any kind of like unintentional integrity issues, they maintain the full mtrie and verify the data as it comes in and verify the state commitment matches the root hash of their tree. And so they're doing a full verification. However, if we start to consume the trie updates from execution sync, they now have a verified set of data. They can verify the hash of the try update and then apply all of those updates directly into their database without having to maintain the full in-memory try. And so that would allow for archive nodes to be built on consumer hardware. And so one of the major barriers with archive nodes is that they have to be on these gigantic, expensive machines. Yeah, and then the verification would look similar to what I've kind of described already, where it gets just the data it needs from the try updates, and then it can verify that against the root blob using consensus data. Another unlock that hopefully we'll be creating some flips about and starting to talk about broadly is streaming and community modules. So as now we have execution data available at access nodes and edge nodes in general, and I think I've said edge nodes a few times, maybe not everyone knows, but edge node refers to access nodes, archive nodes, and observer nodes. So now that edge nodes have access to that data, and there's convenient APIs to use it, it's now possible to build in streaming for some of the event types, or some of the data types. Specifically, events would probably be a very valuable one, but also transaction results, maybe even register updates, account changes, things like that. So there'll likely be some changes to the actual access node APIs, but also the hope is that there will be an ecosystem of community modules. So community teams building out clients and services that are consuming these APIs and refactoring the data into useful things. So think event indexes or account data indexes or different ways to take the data directly out of the execution state and reformat it in useful ways. And then from the changes proposed, I think one of the big unlocks that we would get from further improving the scalability of syncing the data is being able to enable this on observer nodes. So today we have a relatively small number of observer nodes, and I think part of that is because there's not a extremely compelling use case for them, given that they only have local access to consensus data. But once we can enable execution sync on them, now they're going to have local access to execution data, and I think that makes the use case for running an observer much more compelling. And so we'll see, I would expect to see a large growth in the deployment of observers on the network once this feature is unlocked. With that said, the way it's all set up today, the scaling story for getting data from execution nodes out to the public network is not super great. And so if we could enable both of these features, both the selective syncing of data to reduce the amount of data that's actually synced across from the staked to unstaked network, and also spreading the load off of execution nodes to other node types for that initial syncing of data to the nodes, both of those together would would make it scalable enough to the many nodes side of scaling to be able to unlock this to a large number of nodes on the public network. We'll share the slides, I think, but here's a few resources. The top one's the specific flip, where we introduce execution sync in general, pointers to the code, pointers to the protobuf. This last one is we actually have a new Access API that was launched or released with mainnet 21 that allows you to download execution data directly from access nodes if it's enabled on the access node. So yeah, you can check out these links. I expect there to be some more flips coming for some of these changes discussed here over the coming months. So we'll have some public discussion about all of this. And that's the end of any specific content I have. I'm open to any questions or discussions. So anyone have any questions? Yeah, go ahead, Dennis.
I have one question. When we will be able to use this on the edge node side, like from external of the network?
So you're asking when will observer nodes be able to sync the data using Bitswap?
Yeah, observer nodes or like some other stuff we write, like without joining the network.
Yeah. So for access nodes that have enabled it, and the Dapper access nodes do not have this enabled yet currently, you can use that new execution data API. So if you were to say, get one of the permissioned access nodes or the permissionless access nodes in the auction that'll be coming up soon, you could get that on your own access node. I don't have a specific timeline on when we'll actually be enabling it on the public network. I think there's a couple of flips that'll be coming and some discussion about specifically what changes, like how we're going to actually make the changes, and then we'll figure out when that can be delivered.
Okay, thank you.
So yeah, sorry, we don't have a specific timeline yet. Cool. Any other questions? All right. Oh, Peter?
So yeah, I missed the first few minutes of the presentation, so it may be out of scope. But I wanted to ask if archive nodes will remove the need to like go from spork to spork. For example, if I wanted to list all the events from the time that one specific smart contract was deployed, for example, the NFT storefront, would I have to do it by like switching from spork to spork, or with archive nodes it will be like seamlessly?
So that would be like a kind of a separate feature for archive nodes specifically. I think on the long term, there's a desire to take the data from all networks and make it available via a single API. And so I think that would kind of get towards what you're after here. But with that said, there's some technical barriers to get there. And we don't have that work underway at this time. But I would expect that to be coming at some point in the hopefully not too distant future. But as it is today, in the medium term, we're still intending to deploy archive nodes for individual sporks, and redeploy new ones for the next fork. I think there's some technical hurdles to get beyond. One of them being the Trie-less Archive nodes, but there's some other ones just around combining the data and dealing with data formatting changes and things like that.
Okay, I see. Thanks.
All right. If there's no other questions, thank you all for your time and listening. Feel free to reach out to me on Discord. If you're in Dapper, on Slack. I'm Peter A., one of the Flow team members in the Flow Discord. So yeah, feel free to reach out. I'm happy to chat. And yeah, thank you so much.